Welcome to this explainer. Okay, if you're currently staring down a massive computer science exam, honestly, you've come to the perfect place. Today, I'm putting on my insider examiner hat. We're going to give you the ultimate cheat code for mastering one of the most heavily tested, and let's be real, often completely misunderstood topics in all of computer science: CISC versus RISC processors. We're going to break down exactly what these architectures actually are, where students almost always lose easy marks, and precisely what you need to write down to secure those top grades. Okay, let's dive right into our masterclass roadmap. First up, instruction set basics, followed by hardware versus software. Then, cycles and pipelining, compilers and addressing, the modern twist, and finally, we'll wrap up with your ultimate cheat sheet.
Section 1. The instruction set basics. The core difference.
So, first things first, what exactly are we talking about here? An instruction set is basically the complete collection of machine code instructions that a CPU can recognize and execute as part of its fetch, decode, execute cycle. You can kind of think of it as the CPU's personal vocabulary. Now, CISC stands for Complex Instruction Set Computer, and RISC stands for Reduced Instruction Set Computer. At the end of the day, they both achieve the exact same goals, but their core philosophies on how to get there, completely opposite.
Let's look at how CISC operates first. Imagine you want to multiply two numbers that are stored in memory. CISC aims to complete this entire task in as few lines of assembly code as physically possible. So it might just have a single super complex instruction called mult. When executed, this one massively powerful instruction tells the complex hardware to load the two values into a register, multiply them together, and then store the result right back into memory. It closely resembles high-level code, which makes it super easy to program. But because it's doing all of this heavy lifting at once, this single instruction is absolutely going to take multiple clock cycles to finish.
Now contrast that with RISC. That complex all-in-one MLT command, it simply doesn't exist here. Instead, the task is broken down into much simpler commands. You'd actually need 4 distinct lines of assembly: one to load the first number, a second to load the next number, a third to actually do the math, and a fourth to store the result. So 4 instructions instead of 1. But, and this is the absolute crucial part, each of these simple RISC instructions is specifically designed to execute in just a single clock cycle. Moving on to Section 2, hardware versus software trade-offs, the physical reality.
Let's talk physical constraints, because examiners love this stuff. CISC processors require highly complex circuitry and just a massive number of transistors to handle those multi-step, complex instructions we just talked about. And more circuitry means they generate a lot more heat. This is exactly why they usually need dedicated cooling systems, like big fans, making them the standard for desktop computers and laptops. RISC, on the flip side, uses much simpler circuitry and way fewer transistors. This leaves a bunch of physical room on the chip for things like general-purpose registers and cache memory. But more importantly, it uses far less power and runs significantly cooler. This is exactly why ARM processors, which are built on this RISC architecture, currently power over 90% of all processors in use today. We're talking your smartphones, smartwatches, tablets, and even your smart TVs.
But there's a huge software trade-off here. Because CISC completes tasks in fewer lines of assembly code, the overall program is shorter, meaning it takes up much less space in your RAM. RISC uses those simpler instructions, but remember, it requires significantly more of them to complete the exact same task. Longer code sequences mean you simply need more RAM to store all those extra instructions. Back in the day, when RAM was incredibly expensive, CISC was the obvious winner for sure. But today, RAM is incredibly cheap and plentiful, which is a major reason why RISC has become so dominant.
All right, Section 3, cycles, performance, and pipelining, the speed mechanics. Okay, so the absolute crucial takeaway is captured right here in what we call the performance equation. If you really want to impress an examiner, definitely use this phrase. Basically, CISC attempts to optimize performance by minimizing the number of instructions per program, but it sacrifices the number of cycles it takes to run each of those instructions. The RISC philosophy does the exact opposite. It minimizes the cycles per instruction, really aiming for just 1 clock cycle per step, but at the cost of having a much higher total number of instructions in the program. It's a total balancing act.
Now, please pay super close attention to what I call the pipelining pitfall. Pipelining is a clever technique to speed up the processor by overlapping the fetch, decode, execute cycles of different instructions. And here is exactly where students lose marks on exams. CISC instructions have variable lengths and variable execution times. Some are quick, some take many cycles. This makes CISC highly inefficient for pipelining. It just kind of jams up the works.
RSC, however, has fixed size instructions that take a uniform amount of time to execute. Again, one clock cycle. This predictable, steady throughput makes RSC absolutely perfect for pipelining. Do not forget that difference. It's a classic trick question.
Section 4. Compilers and addressing modes, the A-grade details.
Let's look at compilers. As you probably know, a compiler translates your high-level programming language into machine code. For CISC, the compiler actually has a pretty easy job. Since CISC assembly instructions already closely resemble high-level code, there's very little conversion work to actually do. But for RISC, the compiler is incredibly complex. It has to take a single high-level command and completely break it down, doing heavy conversion work to map it perfectly to those dozens of simpler single-cycle assembly instructions. Basically, RISC shifts the heavy lifting away from the physical hardware and places the burden squarely onto the software compiler. A classic exam question here is, explain why a RISC processor requires a more complex compiler than a CISC processor. Your answer absolutely must highlight this exact shift of burden from hardware to software.
Now let's see how this all builds into memory addressing. CISC instructions often include a huge variety of ways to access memory. We're talking modes like immediate, direct, indirect, and indexed. In fact, some CISC instructions are so incredibly niche they rarely ever get used in the real world. RISC, true to its name, completely reduces this complexity. It keeps addressing modes simple, usually limited to just a few specific types. This ensures that every single instruction in its smaller set is used regularly and efficiently. So, if a test asks you to compare the memory addressing modes of CISC and RISC architectures, you need to clearly state that CISC has highly varied, complex modes, while RISC limits them to a simple, heavily utilized few.
Section 5. The modern blended processor. The examiner's trick. Now, if a question asks you about modern desktop computers, you really need to know this. Intel's x86 processors are basically the very last major CISC architectures holding out today. But if you dig a little below the surface, they actually implement something called microcode. This essentially breaks down their complex CISC instructions internally so they can operate in a RISC-like fashion. It's wild, right? They get the high-level ease of CISC software, but they actively leverage the pipelining and single-cycle benefits of RISC hardware. Literally mentioning microcode on an advanced question is a surefire way to prove to the grader that you truly understand the modern computing landscape.
Section 6. Final exam cheat sheet, securing the marks.
Okay, let's lock in those marks. You'll definitely want to use this summary for your revision notes. For hardware and heat, CISC is complex, hot, and needs fans. RISC is simple, cool, and low power. For RAM usage, CISC uses less RAM because of shorter code, while RISC uses more RAM because of those longer code sequences. And for typical devices, CISC dominates desktops and laptops via Intel x86, whereas RISC dominates over 90% of literally everything else, smartphones, tablets, and smart devices via ARM.
And here is your golden ticket. When examiners are marking your papers, they're literally just scanning your answers for these exact keywords. You absolutely must mention that RISC aims for a single clock cycle. You must contrast CISC's variable length instructions against RISC's uniform ones. When you're discussing software, mention compiler complexity. Always bring up pipelining when talking about efficiency, and for that elusive top grade, drop the term microcode when discussing modern Intel processors. Hit those points, and you're golden.
I'll leave you all with this final, kind of provocative thought. If the only major CISC processors left in the world are secretly relying on microcode to act exactly like RISC processors under the hood, will this strict distinction between these two architectures even matter in the computers or the exams of the future? It really makes you wonder if we're just moving toward a totally unified architectural philosophy. Thank you so much for joining me for this explainer. Good luck on your exams, and keep asking those deep questions.